We will simulate this module using a test bench. Please download the test bench template from your e-learning, then add it in the model sim project. Add existing file. Open it, then you can see this is the template or the most generic structure of a test bench. The first line is telling the size of one time unit in this test bench. In this case, it is 1 millisecond, and the other value is the accuracy. Then it gives the module name, test bench, and later we will put registers to give input value into our test module, which is this module, the one that we just finished, and then wires to drive out value that we get from the test module. It then followed by only one block, which is initial block, begin until end, and we need to give name to this initial block. Within the block, we declare a few variables. In this case, two integer variables are going to be used to point to two text files that you can name as you wish. And make sure we are opening the file as write mode. The first part is actually to save the simulation data as binary, and the second one is to save the data as decimal. Later, you will need to edit this so that you can save the unsigned decimal data, the data that you do not divide by 256 to cater for fixed point. Once you make the app open call, you can refer to the file using the pointer only. And this line is the line where we place the simulation value. The use of this function is very much similar to the use of printf or fprintf in C or C++. After all simulation done, we need to close the files and then a finish label. And then at the end, usually we declare an instance of our test module. First, let us instantiate the module that we want to test into this test bench and configure it to match the test bench. Copy the header of the module that we want to test. This is the module, so we give a name to the module, let's say M1. Then we remove all the declaration statement and the comment. Then we put dot operators in front of the input-output variable to indicate that this belongs to the instance module. Then we put empty brackets next to the input-output variable so that later we can put wires or registers from test bench to connect to. Then in the bracket, we put the register names and wires, most likely the same name as the input and output port in the instance parameter so that it won't confuse us. And this will be the registers that give the input to the input, or the wires that read out the output. And the same names that we are giving will not clash to each other because those names started with dots belongs to the module that we instantiate, while the name without the preceding dot belongs to the test bench that we are defining now. Let us save at this point. Next, we need to declare the registers to this input and the wires to these outputs. Like this, registers will be holding the input that we give to the module that we are testing, and the wires will be getting the output value from the module. Then we can give the value to the main input x, y, z. Let's say we want this decimal with fraction. We need to convert to 16.8 fixed point notation like this. And we have an option to write it as 24-bit decimal like this. Use the same calculation that you used before in the module that we want to test. Next, we set the clock waveform. We give clock 0 and then 1 and then 0, 1 and so on. This is very similar to the way we give clock waveform in quarters 2. But now we are giving it as values of 0 and 1 instead of waveform. And it is followed by hash 1 like this to indicate that we want to stop for one time unit that is indicated in the time scale line at the beginning of our file. So we are planning to have one clock before start signal and start signal to be 2 clock cycle and 3 or 4 or even 5 clock cycle after start signal going back to 0. That should be enough for our formula. So then we add the value of start accordingly, 0 in the first clock cycle and then 1 during the next 2 clock cycle and back to 0 in the rest of clocks. Now we can put app display lines at the point where we want to read the output. We need to decide what we want to print. Based on what we have done so far in our formula module, we only code until the first two multiplexer. So let us probe to see if the two multiplexers give the proper output to multiplication wire and multiplier wire. This is how we display the value that we want using app display function. We call the function and then we give the pointer to the file and then we put in the string that we want to display with a few percent placeholders, just like printf. So we want to print the value of x in binary, y and z also in binary, and we also want to print the value of multiplicand, but we precede with m1 dot to tell that this multiplicand belongs to the module that we instantiate. The same to multiplier. M1 is the module that we instantiate, which is the one down here. And we also want to print the simulation data in decimal with fraction. So now we replace the %b with %f, and in between is the size of 10 character with 4 decimal point, the same to all other variables. And the variable that we want to print, x, y, z, multiplicand and multiplier, we have to divide them with 256.0 so that we get the decimal value with fraction. Let us do this process of capturing simulation result at the end of every clock cycle. It is time now to save this test bench and compile and start the simulation. Successful. Both compilation have to be successful before we can start simulation. To start simulation, choose the project that you are doing now and choose only test bench because our simulation is being done in test bench. When the test bench loading is successful, what you need to do is just to press run all to start the simulation. When you get this question about wanting to finish or not, say no and wait until it stops at the stop level. Okay, stop at the stop level in the test bench. At this point, we can restart. Then we can look at the result in the text file that we have saved using app display. Now you see these are the two newly created text files. We can look at the binary file first. This is how it looks like. The value of x, y, z and multiplicand. To be easy, let's look at the one in decimal. You see this first line is when start is 0. This is when start is 1. We should get at multiplicand the value of x and at multiplier value of y, but instead we get the value of z. This is an indication that our code is wrong, and obviously we can look at our code here. Our multiplexer is multiplexing x and y in the first multiplexer while we should be multiplexing x and z. Our diagram clearly shows that we want to multiplex x and z and y and square root of pi, but our code is multiplexing x and y. So the diagram is correct, but our code is not so correct. Again, our code is multiplexing x and y instead of x and z. This must be corrected. So to go back to editing, we need to stop or end simulation. It is advisable to stop simulation and do the editing in editing mode.